Hello everyone. Today I'm going to introduce this exciting open-weight model DeepSeek V3, which is the top one open-weight large language model, and it outperforms an older version of ChatGPT 4.0. DeepSeek team also released a technical report of 53 pages, and I will break down the key takeaways for you to understand it easily and quickly. Okay, here is the outline of my presentation. I will first present to you the performance of the model and tell you some basic information about the DeepSeek V3, particularly the most essential details and what improvements it made over the older version DeepSeek V2. And then I will talk about the more details on the techniques for its improvements on the performance, memory efficiency, and computational efficiency. Okay, so about the performance. On educational benchmarks, it outperforms all existing open-weight models and achieves performance similar to Claude 3.5 and ChatGPT 4.0. And on coding, math, and reasoning, it achieves state-of-the-art performance among all non-long chain of thought open and proprietary models, and it even outperforms O1 Preview on specific benchmarks such as Math 500. So here is a diagram that shows its performance. The blue lines indicate the DeepSeek V3's performance, and as you can see on all benchmarks, it achieves either top 1 or top 2 performance. For about 3 benchmarks, it performs slightly worse than Claude 3.5 Sonnet, but overall it ranks top 1 and outperforms ChatGPT 4.0 May 13th on all of those benchmarks. And its performance is also confirmed by the ranking of LLM's arena. So on this leaderboard, we can see that DeepSeek V3 indeed outperforms GPT 4.0 2024 May 13th, and it also surpasses Claude 3.5 Sonnet. Alright, so this is why this model has attracted so much attention. And then here is some basic information about the model. Its architecture is a mixture of expert transformer architecture, which is consistent with previous DeepSeek models, and the model size is 671 billion parameters. So it is the largest modern and performant language model. As a mixture of expert transformer, not every parameter is used for each token. So only 37 billion parameters are activated per token, which means its inference speed should be roughly at the level of 37 billion parameter dense model, although the memory consumption to store the full model parameters is still at 671 billion parameters. And the model is trained on 14.8 trillion high quality and diverse tokens, which is similar in scale to Llama 3 series models. And the final contact length of the model is 128K tokens. It was trained on 2.788 million H800 GPU hours. So the total cost is roughly 5.576 million US dollars, which is much cheaper than training ChatGPT 4.0. And the model is trained with an FP8 mixed precision training framework, meaning it uses only 8 bits of precision, so during inference we don't need to worry about reduced precision when the model parameters are expressed with only 8 bits. Here are the major improvements over V2. So it uses an auxiliary loss-free strategy for load balancing. It is trained with multi-token prediction objective. It employs an FP8 mixed precision training. It has improved pre-training data quality, and it uses synthetic data from reasoning models and DeepSeek 2.5 for post-training. Okay, now let's talk about the techniques. What is the use of multi-head latent attention? So it is a technique to achieve memory efficiency and computational efficiency. Here is how it works. Let HT be the input to the attention layer, then it is mapped with WDKV to CTKV, which is a low-dimensional vector. Essentially, it's a compressed version of the original HT. When we want to calculate the key value vectors, we use other matrices like WK to map it back to high-dimensional space. Another difference from normal attention is that they apply rope to another vector mapped from H, and then they concatenate that one with the key vectors projected back from the low-dimensional vector. Whereas usually rope is applied directly to the key vectors. And the value vector is also projected from C with another matrix. So it's decompressed from the low-dimensional vector as well. And then another thing they do is to map the query vectors into a low-dimensional vector CTQ as well, because they want to reduce activation memory during training. When using gradient checkpointing, you don't have to store all intermediate results. You just need to store some of the activation values, and then here we store the low-dimensional CTQ. So this will save some VRAM during training, even though in inference you don't need that. Okay, so this is about multi-head latent attention. Now about the DeepSeek mixture of expert with auxiliary loss-free load balancing. So mixture of experts generally means there are multiple feed-forward neural networks at the same level in a block, but only a small proportion of them are used for each token, and the results are aggregated as the weighted sum of the outputs from those experts. Here, the special design from DeepSeek is that they have two types of experts. Some are shared among all tokens, and some are selected only for a small proportion of the tokens. Below is how they compute the weight or gate for each expert for a token. The weight depends on the centroid vector of the routed expert, represented as EI, and its dot product with the input vector UT, which is the representation of token T. This is the affinity score of the expert to the token. So it determines how important each expert is to a token, and the relevant expert is used for the calculation of that token. So the way they achieve load balancing of experts is not based on adding a training loss. They don't want that load balancing as part of the training loss, because adding an auxiliary load balancing objective can distract the training from achieving optimal model performance. So instead, they add a bias term BI to the routing gate of each expert, SIT, which is the relative affinity score of expert I to the token T. So if an expert is underloaded, which means they receive fewer tokens, its bias is increased, while if it's overloaded, the bias is decreased. Additionally, there are some extra techniques like complementary sequence-wise auxiliary loss. That means even though they primarily rely on auxiliary loss-free load balance, in extreme cases of imbalance, they apply a penalty. And there is also a node limited routing, so each token is sent to at most M nodes to limit the communication cost. and they have no token dropping during training because of this balanced approach. They also apply specific deployment strategies, so there is no token dropping during inference. Another technique they use is multi-token prediction. So at each step, instead of predicting only one token, they predict multiple tokens. This figure shows how it works. On the left, you see the major modules of the main model, which processes the input tokens through multiple transformer blocks and then produce an output layer. And the top layer representation is then forwarded to the next step for the prediction of the second token. So it is concatenated with the original embedding of the input tokens. Here you can see each of them is applied with an RMS norm layer, then those two vectors are concatenated, followed by a linear projection. After that, there is a transformer block only for the MTP module, which then feeds into an output head. The output head and the embedding layers are shared between main model and the MTP module. Then the output of the transformer block is used in the next step of predicting the subsequent tokens. Okay, yes, so this is the multi-token prediction approach, but it's only used during training to improve the model's performance through forward planning. During inference, they discard this module and just use the main module to predict tokens one by one in the usual way. Okay, that's the performance improvement technique. Now let's talk about techniques used during pre-training. One important aspect is data construction. So they increased the ratio of mathematical and programming samples, which I believe is the key to their high scores on benchmarks. And they also expand multilingual coverage beyond English and Chinese, introducing more languages into the pre-training dataset. Another important detail is their learning rate schedule, which differs from general schedule like we see in models, the model trainings like Llama 3 or Quinn. Their approach is as follows. They first linearly increase the learning rate, which is a typical warm-up steps for only 2K steps. And then they keep it constant until 10 trillion training tokens. So this is different than general practice where the learning rate decays. And after that, they gradually decay it by a factor of 10 over 4.3 trillion tokens, then maintain a reduced constant learning rate for 333 billion tokens, and finally uses an even smaller learning rate for the last 167 billion tokens. So this is again different from methods like training Llama and Quinn, where they often decay the learning rate to zero in the last few hundreds of billions of tokens. I think this is an experimental finding that constant learning rate at some point yields better learning efficiency. And about the batch size, for the main pre-training, they use a context length of about 4K tokens, and they gradually increase the batch size from 3,000 to 15,000 during the first 469 billion tokens, then keep the large batch size fixed for the remaining training. This makes sense because at the start you don't need an enormous batch to learn basic patterns, and a smaller batch might allow no more update steps for the same compute, and then it can speed up early training. And for the long context extension, they apply yarn, which is a technique to adjust the rope base value for the desired context length, then fine-tune the model for a certain amount of data. They do this extension twice. Once it's from 4K to 32K, and then from 32K to 128K, each time fine-tune the model for 1,000 steps. Then about post-tuning, Specifically, supervised fine-tuning, they use 1.5 million instruction tuning samples in total during post-training, and they incorporate synthetic reasoning data. For math, code, completion, or logic puzzles, the supervised instruction tuning data is generated by DeepSeek R1, which is like the O1 reasoning model. It uses a long chain of thought to produce an eventual answer, but here they only train the model to produce the final answer, not to generate the entire chain of thought. And they also use synthetic non-reasoning data for creative writing, role-play, and simpler QA tasks generated by the previous frontier model, DeepSeek V2.5, and they have human annotators to verify the data to ensure the quality. And for this phase, their learning rate uses cosine decay from like a 5 times 10 to the minus 6 down to the 1 times 10 to minus 6, which is a useful reference if you ever want to fine-tune your own large language model. About the post-training part, they also employ reinforcement learning, so their reward model includes both the rule-based component and the model-based component, and they use group relative policy optimization rather than PPO. So if you want to know more details on this part, you can check their technical report or the original paper that introduced this approach. So those are the major takeaways or the most interesting points about the DeepSeek V3 training. From their website, you can try DeepSeek Chat for free. They are pretty generous, and you can also pay for APIs, which are extremely cheap. See, for 1 million tokens, the input cost is only $0.014 if it's a cache hit, and $0.14 if it's a cache miss, and $0.28 for 1 million output tokens. Yeah, so this is really affordable for personal or enterprise use. Thank you very much for watching.